Welcome back. Let's pick up with our discussion of intermolecular forces with the London dispersion forces. So as you can see here in the first bullet, these are the weakest of all of the intermolecular forces. If you're nonpolar, these are the only intermolecular forces you get to have. Now, just because they're the weakest does not mean that they are inconsequential. It actually turns out that dispersion forces can tally up to be more total strength than something that has dipole-dipole forces. It's the whole, kind of like an ant in an ant bed. If you get bitten by one fire ant, it's not a big deal. But if you get bitten by the entire ant bed, now you're in trouble. And that's kind of the way LDFs work. If you have just a one little molecule LDF, it's okay. But if you have something that's really accumulating, the LDFs can be really important. The thing about the London dispersion forces is that for a nonpolar molecule, which this is the most important IMF for, there's no permanent dipole. So there's none of that separation of charge that allows you to be attracted electrostatically. But something kind of strange happens in all molecules. All molecules have the ability to go through what's called an instantaneous dipole formation. Now, instantaneous dipoles occur when an electron cloud gets distorted, when it gets beat up. And that can happen just from the probability of the electrons flying around ending up on one side or the other, or it can happen through collisions where the electron cloud gets bent and distorted. But when that happens, an instantaneous dipole forms. You break the symmetry and you have a positive negative pole that lasts for a fraction of a second. It's very, very fast, and then it just kind of bounces back to its normal shape. But in the meantime, it creates a cascade of instantaneous dipoles that ripples throughout the entire substance. So let's take a look at how an instantaneous dipole could form. We're actually going to look at helium, which is the hardest substance that we would try to involve in this process. But look here at this helium atom 1. Normally, helium has 2 electrons, and they are on opposite sides of the nucleus. So there's symmetry there, and it's nonpolar. But if something happens, the electrons happen to end up on the same side, either through probability or maybe they collide with one another. If the electrons end up on one side together, you're going to have now an instantaneous dipole. Helium atom 2 here is not nonpolar. When the instantaneous dipole forms, if you go over here to B now, you can see that we lost that symmetrical shape and we go to sort of this oblong shape indicating electron density, where you have all the electrons over to the left where they're together, and then around the nucleus there's hardly any electron density at all. And that's going to cause a neighbor to become instantaneously polar as well. When they're in this transitional state, there can now be an attraction, just like we saw with dipole-dipole, between the partial positive and the partial negative sides of the molecule, or in this case, of the atom. Again, this does not last very long. We're talking microseconds or less, but it ripples throughout the entire substance. No matter how many billions of molecules or atoms there are, it will eventually affect them all and then come back around. Kind of like the wave. If you've ever gone to a sporting event, you see the wave go around and around the sports stadium. That's kind of the way that instantaneous dipoles ripple through a sample of a substance. Now, for London dispersion forces then, not all are created equal. Some substances, it is much easier to create the instantaneous dipole than it is for other. We have a new vocab term for that. You'll see it here in bullet number 3. That term is polarizability, the ability to make polar, to form the instantaneous dipoles. This is a word that you need to learn how to use to answer chemistry questions, especially those that involve London dispersion forces. So what determines a substance's polarizability? There are really two things. The two things are the shape of the molecule. If it's a long, skinny shape, it's easier to distort than a more compact, rounded off shape. And the other thing that affects polarizability is the size of the molecule. And it's not really the nucleus getting bigger that makes the difference, it's the size of the electron cloud. The more electrons you have, think of a larger, puffier cloud in the sky, it's more distortable with the more electrons there are. So a lot of times we answer questions about polarizability, like why is this one more polarizable, by starting out saying this is a larger atom or a larger molecule, it has more mass, and so therefore we understand together if there are more protons adding to the mass, then there has to be more electrons, which makes the electron cloud larger and more distortable. So we can see here that the dispersion forces increase as molecular weight increases. I just got through explaining that a little bit. London dispersion forces are in all covalent molecular compounds. They're in all molecular covalent compounds. If you're nonpolar, this is all you get, LDFs. If you are polar, you get LDFs, and then you also have your dipole-dipole forces, and maybe hydrogen bonding if you have those qualifications. Just because you're polar doesn't mean your dipole-dipoles are going to add up to be more than your London dispersion forces. Really, the only way we can tell is to do some experimentation and see where things fall out. So again, it depends on the shape of the molecule, and it depends on how many electrons are in the molecule or the atoms. So here's a last little slide here to illustrate how shape matters. We have N-pentane and neopentane. Both of these molecules are C5H12. So they have exactly the same chemical formula. They would have exactly the same mass. So mass is not important here in explaining why they would have different physical properties. In this case, it's all about the shape. I hope you can just look at this and inherently understand that the N-pentane on the left, and it's more what I call like a sausage shape or a hot dog shape, is more distortable, more bendable, more flexible than the rounded off neopentane on the right, which I kind of refer to as like a hamburger shape. We all know from our practical experiences that hamburgers are less flexible than hot dogs. Hot dogs are floppier. If you don't believe me, go home and try to flop a hamburger. It doesn't work that well. But when you're doing that, you're creating an instantaneous dipole by changing the shape. So shape is very important. When it comes down to deciding whether London dispersion forces are going to be more important than dipole-dipole, you need to look at the mass. When the masses are close to the same, they don't have to be exactly the same, but when they're in the same ballpark, dipole-dipoles are almost always stronger than LDFs. But if you have two substances that have drastically different masses, oftentimes the one that's more massive is going to have substantial London dispersion forces, usually overtaking dipole-dipole in terms of strength. And I use the word usually there because you never know. These are just kind of generalized rules of thumb. All right, well, that's explaining London dispersion forces and polarizability. Our next step is to start doing practice by picking out what IMFs are present and then start answering questions about physical properties. If you didn't understand this discussion on LDFs, come see me and we'll iron it out.